This week we are studying pretty much sky motions and gives you a sense how the sky looks like as seen by somebody standing on Earth. And there are three types of motion or three basic motions you all should be aware of. One is, let me go to Starry Night software. So you have the same capability of reproduce what I'm going to do here in Stellarium, the software you should have downloaded by now. But here are the three basic motions we are subjected to. One, if you are facing south, if you are in the northern hemisphere, like in San Jose, and you are San Jose, and you are facing south, if you keep staring outside, you don't see, apparently, you don't see any motion going on. But if you have the ability of speeding up the time flow, as you can see here, 5, 12, 15 a.m., 16, so the time is flowing 1 second each time, or each second. So if you have the ability of speeding up this flow, this time flow, then you might be able to start seeing something happening, and that's what we're gonna do now. Look at that. So as being the northern hemisphere, if you're facing south, what you see is sky objects, the star, the moon, the sun is coming up anytime. Look at that. They all rise in the eastern sky, and rising is a technical term that means objects appear to come from below horizon, and here's your horizon, to above horizon, and they set in the western sky. So right now we don't see anything because it's daytime, but since this is a software, I'm going to get rid of daylight. There you go. So it's 9 a.m., but I got rid of daylight, and if you look pretty much in the western sky, you're going to see Aldebaran going down, the Pleiades are going down. So here and there you see some kind of a dots moving in an erratic way. So they are satellites, right? Artificial satellites, handmade satellites, and Orion is setting. So setting always occur when objects goes from above horizon to below horizon, and in the northern hemisphere you see this happening in the western sky. So this primarily happens because Earth rotates on its axis of rotation from the western sky towards the eastern sky. So in the space, Earth is rotating like this. And as a result, we see the entire sky going from east to west. Okay. The other motion is Earth revolution around the sun. And in order to mimic this motion, here's what I'm going to do. I'm going to stop this now, and I'm going to change to sidereal day. So sidereal day sidereal is a word you should be also be learning. Is always with respect to the stars, right? So pretend for now that we have the ability. So let me show the ecliptic line. The ecliptic line is a line that is pretty much created by the sun's path in the sky, as apparently seen by somebody here on Earth, but is also the name of Earth's orbital plane around the sun, the plane that is defined by Earth orbital motion around the sun. So what I'm doing also here is displaying the location of all planets and some asteroids and some important objects. Okay, so The time now will be flowing one sidereal day each time. How does this work? So what is sidereal day? Sidereal day is the time take Earth to complete one rotation around its own axis of rotation. So imagine that you look up in the sky and then you see the sun. No, you see a nice constellation here. Wait a second. See if I can locate one. Um, not yet. Not yet. Not yet. Let's see. Okay, look at this. This is a beautiful um, group of stars: Taurus, Pleiades, and Orion. See these three groups? Move them up. So Pleiades, Taurus, and Orion. And you have Betelgeuse, you have Rigel, Bellatrix, and Scythe. This is Orion region. So just for now, imagine we have the ability of facing the sky like you take a spaceship, right? And you go above Earth surface and then you keep staring at this region always. And so you open your eyes and take a shot of it, close your eyes, and then open up again in one sidereal day, which is the equivalent of not one day, but 23 hours and about 56 minutes. Okay? It's not 24, it's about 23 hours and 56 minutes. You got it? So during this time, exactly Earth gives one turn with respect to the faraway stars. Meaning that every time you open your eyes, you should be able to see the same sky region in respect to your horizon. So which means you're going to see, of course you don't have horizon if you are up in the space, but you know what I mean, right? We can't do this on Earth because we have an atmosphere and everything gets messed up. But imagine you could take a picture of your horizon, move up to the space, put your horizon right in front of you, and then keep opening and closing your eyes every 23 hours and 56 minutes. Look what you would see. Sidereal day. So open your eyes. There you go. Now close your eyes and open again one sidereal day later. Any change? Did you see anything happening? Let's do it again. And again. And again. So what's happening? Well, I'm seeing the moon kind of drifting some amount of degrees every sidereal day from the western sky towards the eastern sky. Let's keep doing this. Any other changes? Now let's keep up doing this, but a little faster. And you'll see the time is going to run crazy. See, the moon is keeping going fast. Now look at the sun. The sun is also coming from western sky to the eastern sky. And the planets have all kind of a weird motion. So in fact, the word planets was invented by ancient astronomers to indicate certain stars. They thought planets were stars. Certain stars in the sky that had erratic motion, as well as the sun and the moon. So all the other stars, if you keep observing and keep track of their position in the sky, I mean, they all shift east-west, as we saw, as a result of Earth's rotation. So they knew that. But if you keep taking pictures, or in olden days, perhaps making a map of the star's position very consistently every day, you notice that the stars keeping always with the same apparent position with respect to each other, except the planets, the sun and the moon. And that's why they readily notes 7 objects in the sky that had erratic motion: sun, moon, Mercury, Venus, Mars, Jupiter, and Saturn. 7 objects who later on became sacred and called gods. And the whole astrological system, which was pretty much common and important in those days, was invented by the Mesopotamian people in some ways. In India was slightly different. In China it's slightly different. In India it's more focused on the moon's path, and in Mesopotamia it's more focused on the sun's path. So why is this happening? Because Earth is going around the sun. So the sun sometimes is seen. Let me stop when the sun there. So sun sometimes is seen against the constellation of Taurus. But if you wait a few days later, the sun is not seen anymore against the constellation Taurus. This is because of Earth revolution around the sun. Now, another way of saying Earth revolution around the sun is, by somebody here on Earth, is the following. So let's change this to days, like a normal day, right? In fact, let's do differently. No, 300 times, no, 400. Okay, look at this. I would like to keep track of this ratio here, right? Mercury is right. No, forget about the planets. Look at Taurus and the sun. And look at this star right here, Zeta Tauri. This star, Zeta Tauri, a variable star. Okay, so let's keep track of the sun in respect to these stars, and let's move one day at a time. So here is 11:20 a.m. on June 13, 2030. Oh my goodness. So let's go one day after, June 14, 11:20, and then June 15. So you are going one day at a time. So now imagine you have your clock or your watch, and you set a given time, and you set a particular day. Let's change this to 2016. That's better. So 2016, you have Taurus in there. Zeta Taurus over there. The sun is right here. Okay. And why not September? September what? Today's today. September 14. There you go. That's today. So today, now we lost our Taurus. Well, yeah, we lost our Taurus and lost our reference. Which star is this? Sigma Leonis is right there. How about, no, this is Jupiter. I want a star. How about this one over here? There you go, the nebula. It's a double star. So let's keep track. Of course, we can't see the nebula and the sun together in the sky like that because the sun is too bright. In fact, don't forget we have a daylight, right? So that's what we would see if we had a proper solar filter. But so let's keep track of the nebula and the sun and move up one day at a time. Look what happened. So each day, in respect to your horizon, the sun is basically in the same position. So in respect to the mountains, to the building, at 11:20, the sun is in the same sky position, as you well know. So you wake up 10 in the morning, and the sun is, in respect to your horizon, is kind of in the same spot. But if you could look at the stars would be a little bit more to the west, right? So why is that? Well, it's because there is a difference between the sidereal day and diurnal day. One is 23 hours and 56 minutes, about that, which is the sidereal, and the other one is the diurnal day of 24 hours. So stars, they complete one apparent turn around Earth faster than the sun. So if you make a bet between the sun, see there is a star right here, Porrima. Never heard of this star. So you have in fact, let's okay, look at this. The star, the sun, and the star Porrima, right? So in one day later, Porrima is more to the west than the sun is. And so if you mark a line and make the sun in Porrima make a bet or a race, see who completes a turn around Earth, as seen by Earth. So they don't turn around Earth, but the Earth is the one rotating. But if you don't know about it, if you are 3,000 years ago or 5,000 years ago, and you have the ability of mark these positions, and you could put a star and the sun together in the sky, and then say, okay, I'm going to close my eyes and open again. What you would see is the stars, not the sun, the stars seems to complete an apparent turn around Earth faster. And that's because there is a difference between the so-called sidereal day and diurnal day, or tropical day. And the sun kind of takes longer, about 4 minutes to do the trick, to do the turn. And so the stars, every day, they move a little bit more to the west than the sun does, right? As seen by somebody here on Earth. So as a result, which means in respect to the stars, as we saw in the previous animation, the sun seems to be going eastward every day, right? And why is that? It's because Earth is the one revolving around the sun in its direct and prograde motion. The third apparent motion is precession. Precession is caused by the combined tug of or pull of Earth, of moon and sun on Earth equatorial region. So Earth is a little bit bulging as a result of that, and this pull make Earth wobble in space, and it takes quite a while for Earth to complete one turn as it wobble. It's about 26,000 years, right? And precession can only be or could only be found when you compare positions of sunrise in the sky over long periods of time. So you have to have records of where the sun was in respect to one of the equinox or solstices, and keep track of this position over hundreds of years. So you have to, in fact, it was found. Hipparchus was one of those who discovered. So we have to find records in the past. So Hipparchus had access to information in those days, and you have to have information on where the sun was in one of the equinoxes or in one of the solstices. And then you realize, well, nowadays the sun is not there. It's because the sky is changing, and then you go back and pull up records, and then you realize there is this wobble motion called precession. Okay. This is one thing I'd like to highlight. If you need some of that to do your go back here to do your exercise with the moon. So what is the exercise with the moon? I'm gonna go briefly here with you. Let me go. In fact, I want to find the moon. Wait a second. So the sun is coming up, September 14. And there's the moon there. Okay. So let's say you keep track of the moon and you see the moon in the time that I suggested in Stellarium, right? And you can see which phase it is. So in this case is obviously a gibbous phase, and you see the right hand side of the moon is sharper than the left hand side of the moon, which means the sun is somewhere here, which means this is a waxing position. So keep track of the time, 12:29 a.m. So if I go to 1:29 a.m., where the moon is going to be in respect to your horizon. If I go to back to 12:29 a.m. So where the moon is going to be 1 week after or the next day with respect to the original position, and where the moon is going to be 1 week later, 22, with respect to original position. Well, where's the moon? In which phase is going to be? So this is what you have to do in Stellarium. So if you have any question, you can join us in the chat room on Thursday, and I will try to reproduce this. But that's the only way you have to do in order to be able to complete the exercise. So again, for the Stellarium assignment of this week, you must download the software. If you have any problem, let me know. In the chat room last week, I stayed over 1 hour with one student to make sure the download was successful. She had a Macintosh and there was some problems going on. No, she had an HP. It was not a Macintosh, it was an HP, I think. No, it was a Mac. It was a Mac. So each computer might have some little glitch, and we can. I'm not a wizard, but computer wizard, but I might be able to give you some help. If not, you can always use a computer at Evergreen. So let me know, and please join us on Thursday at 7 o'clock, 7 p.m. in our chat room. Okay, bye.